Hello, I'm Bernhard Kragel, and this talk is about the Civl Verifier, which is joint work with Shaz Kadir. Let's start by looking at a very simple concurrent program, where we have a shared variable x that is initialized to a constant n, and then there are two concurrent threads that both first acquire a log L, then they read from x, then write back the value they read plus 1, and then they release the log. What you want to check for this program is that when both threads finished, we have that x is equal to n plus 2. A classical approach to do this verification would be to convert the program into a transition relation with an initial state predicate, a next predicate, and a safety predicate. And then we would have to invent an inductive invariant over this transition relation. However, this is complicated for a number of reasons. One is that by going to the transition relation, we lose a lot of structure from the program, and forcing the programmer to think in terms of the transition relation hinders productivity. And second, the inductive invariant over the transition relation is likely to be complicated because it needs to do a lot of case distinction when reasoning about the low-level encoding. Now, let's look at an alternative approach. What we see in this program is that there are two critical sections that are protected by the same lock. So we might want to reason that both of these threads actually execute atomically, and we don't want to consider any possible interleavings between these two threads. Now, by having both of these threads execute all of their operations atomically, we actually realize that the log L is not necessary anymore. And so we could convert the program into one where we actually just have two atomic updates to X. And by looking again carefully at this program, we see that it actually does not matter in which order these two threads execute. We can just pick one order and arrive at a completely sequential program for which we can easily generate a verification condition and give it to an automated reasoning system to discharge this verification condition. Now, verifying our simple example with these many small steps might look silly, but this is of course only the tip of the iceberg. If we turn our attention to realistic implementations of large concurrent systems, then the task of specification and verification quickly explodes in complexity. To combat this complexity, the Civl Verifier advocates layered refinement. Instead of proving a low-level program P1 directly, we construct a whole sequence of programs, P2, P3, up to Pn, where each of the layers becomes more and more abstract until we reach a high-level specification. The key of this chain is that each of the steps corresponds to only a small simplifying program transformation that is justified by a simple proof artifact like an inductive invariant, which is much simpler than an invariant that would have to be specified for the low-level implementation. A second key decision in Civl is that each of the program layers remains a structured program, meaning that we never expose a transition relation encoding to the programmer. The language of each layer stays the same. The only thing that changes is the granularity of atomic actions. While the low-level implementation might just use atomic CPU operations like reading and writing memory, the high-level specification might specify atomic operations that reach consensus in a whole distributed system in just a single atomic step. And finally, Civl has a syntax called layered concurrent programs that allows the specification of all program layers and their connecting proof steps in just a single syntactic artifact that avoids any repetition between shared parts of the program layers. Now, in the rest of this talk, I'm first going to illustrate some of the program transformations or proof tactics that can be used to connect different layers, and then I'm illustrating the layered concurrent program syntax. The first tactic I'm going to show is the creation of atomic blocks, like we did for the lock-protected critical section in our introductory example. Civl justifies this creation using a theory of commutative atomic actions. So the programmer would specify so-called mover types, like here the acquire is a right mover, release is a left mover, and reading and writing under lock protection is both a left and right mover. Now Civl checks that these mover types are valid by doing pairwise commutativity checks, and then applies a reduction theorem like Lipton's reduction to justify that executing the operations atomically actually does not lose any concurrent behaviors. The second tactic is the creation of atomic actions. So on the left here I have a procedure acquire that repeatedly calls a compare and swap operation to set a Boolean variable from false to true until it succeeds. So the compare and swap would fail if B is currently equal to true. And our goal here is to convert this procedure into an atomic action that just blocks until B is equal to false and then atomically updates B to be true. Now the issue here is that the acquire procedure can be interrupted at many points to yield to other concurrent threads. And now the justification to say that that this acquire procedure can actually be summarized to the atomic action is that that Civl shows that all of the executions of this acquire procedure actually behave like skip star, acquire, skip star, where skip is just an atomic action that does not modify the state at all. So it's basically a stuttering step. So if we visualize this, we can see that that each of the failed compare and swap operations actually leaves the state unchanged. When the Boolean variable B is currently true, the compare and swap fails and leaves B equal to true. And only the final compare and swap operation actually does a state update that sets B from false to true. And so we can simulate the behavior of this thread by saying that each failed compare and swap corresponds to skip, and the final successful compare and swap corresponds to executing the action acquire. Now, when doing a layered proof, it is often convenient to change the state representation of the program to simplify the application of subsequent proof tactics or even enable these applications in the first place. Now, what we have here is the same acquire procedure as before, but now we want to prove a different atomic action specification, namely one that ranges over a variable L that is either equal to none if the lock is not held, or it is equal to some thread ID, namely the thread ID of the thread that holds the lock. So to make the connection between these different states, B and L, the programmer is actually allowed to refer to the new state in the original program. So we get this introduced local parameter, and then the programmer can also specify special atomic actions and that are called introduction actions. And here in this example, whenever we have a successful compare and swap operation, we also do the update to the corresponding abstract L variable to set it to some thread ID. And the second thing the programmer needs to specify to actually enable Civl to prove a simulation relation between the procedure and the atomic action is an invariant. In this case, the invariant says that B is false whenever L is none, and B is true whenever L is equal to some thread ID, which is the intended connection between these two different state representations. Now let's turn our attention to asynchronous programs. Here we have a shared variable x, action add to add some amount I to x, and action async sum, which creates n asynchronous instances of add with the parameter I ranging from 1 to n. Now our goal is to prove that async sum can be summarized to action sum, which just atomically increments x by the sum from 1 to n. If we look at the possible executions of async sum, we see that there are many of them, depending on the order in which the individual add operations take effect. A classical inductive invariant would require us to specify all of the intermediate states that can be reached by all of these different executions, which is a huge mess. However, Civl allows us to focus on just a single execution, namely the one that executes the add operations in increasing order, add 1, add 2, add 3, and so on. And the inductive invariant that we need to specify for this really just specifies this order of add operations take effect. So invariant suminf here just says that at some intermediate point j between 0 and n, we have that x was already incremented with the sum from 1 to j, and the remaining add actions from j plus 1 to n are still pending. So it really just specifies the individual intermediate states of this single execution. And we showed that this proof technique actually works for realistic practical protocols like Paxos, two-phase commit, and so on. Let's finish our journey through proof tactics by looking at the foundation for all of them, invariants and permissions. Civl introduced a particular kind of invariants, called yield invariants, which are both named and parameterized. On the left here, I'm showing a yield invariant called yield x that states that the shared variable x is greater or equal to I, and I is a parameter to this invariant. Now, yield invariants are explicitly attached to code locations. Like in the procedure double inc on the right, it is both a precondition, it's called in the middle of two atomic updates to x, and it is also a postcondition. And the key here really is this parameterization, which enables us to instantiate this invariance to the particular needs of a code location. And so non-interference now only has to be proved once per yield invariant, as opposed to once for each of the instantiations of the invariant, which can lead to large speedups in the number of verification conditions that need to be discharged. However, there's still one problem with checking non-interference that I want to illustrate on the code snippet below. So here we have some mutator thread that executes some code to enter a barrier, and so the yield invariant mutator inf states that this thread I is in a variable called barrier set, and afterwards the subsequent code snippet removes the thread again from this barrier set. Now, the issue is that if we want to prove non-interference, let's say if two threads are I and j are both at the mutator invariant, and then we execute this code fragment to remove thread I from the barrier set, we still want to have that mutator invariant holds for thread j. However, without any further information, this does not hold, because I and j can actually be equal, which really comes from this issue that we are combining code from two different contexts. Instead of baking in thread identifiers, Civl actually provides a much more general mechanism of linear permissions. However, here in this example, it is really just enough to annotate these variables to both the procedure mutator and the mutator invariant with linear, and this gives us this free invariant for our non-interference check that states that I and j are actually different, and so in having this extra information, it is easy to discharge this invariant. And so overall, linearity allows us to get additional information into non-interference checks and also commutativity checks without explicitly writing down and propagating these invariants. Recall that I already mentioned that Civl expresses a chain of programs P1 to Pn as well as their connection as a single layered program. This happens through a syntax for data layering and control layering, basically saying which variables live on which layer and which operations live on which layer, such that overall only the changes from one layer to the next are expressed, and the shared parts between adjacent layers don't have to be repeated. The concrete syntax for Civl is a conservative extension of Boogie, where Boogie provides the features for writing imperative sequential code like assignments, loops, if conditions, and so on, and also the associated specification features like pre and post conditions, assume and assert statements, and so forth. Now, Civl, on top of that, adds asynchronous calls, parallel calls, and yield statements to express concurrent programs, and then all of the other annotations it requires to express a proof are given as attributes, which can be attached to basically every abstract syntax tree node of a Boogie program. Let's look at an example. Here we have the declaration of a global shared lock variable L. Global variables can only be accessed in atomic actions, like the action for acquiring and releasing a lock. These look like regular Boogie procedures. However, they have these right and left annotations, which tells Civl to interpret them as atomic actions and also gives the mover type of these actions. In the middle column, I'm showing the compare and swap based implementation of acquiring a lock that we already saw before. This procedure is annotated with the yields attribute to say that it is a concurrent procedure and can be interfered with by other threads. And it also says that we want to prove that this procedure can actually be summarized to the atomic acquire specification. To do so, we connect these different representations using layer numbers. So here on the B variable, we say that it exists from layer 0 to layer 1, and then when going from layer 1 to layer 2, we introduce the variable L. And similarly, we have layer annotations on the procedure to say at layer 1 we want to make this acquire procedure disappear and do the proof that we can summarize it with the acquire specification, which has also a layer range attached to it to denote at which layers these atomic actions exist, which has an impact on the set of commutativity checks that we need to do. We already saw that introduction actions are used to assign meaning to introduced variables. The call to set L here that assigns meaning to the introduced variable L only exists at layer 1 of procedure acquire, where we do its refinement proof. It's not yet part of the concrete layer 0 version of acquire. The yield invariant loginf captures the intended connection between B and L and is attached as both pre and post condition to acquire and as a loop invariant. And finally, we have linearity annotations to express the uniqueness of thread identifiers. Going further, we might have a procedure client that has a lock-protected critical section. At layer 1, these calls to acquire and release are really to the low-level implementations that use compare and swap and the B variable. However, at layer 2, Civl changes those to go to the atomic action specifications and uses the mover types to prove some atomic action specification for the client procedure, let's say called client spec. And this means now going from layer 2 to layer 3, we end up with an atomic action that can actually completely forget that we had a lock, and we just end up with an atomic spec for whatever this procedure does in the critical section. Now that you have an understanding of layer refinement, let me briefly talk about two bigger case studies where we applied this methodology. The first one is a concurrent garbage collector, which periodically scans the heap for unreachable objects to deallocate, while concurrent mutator threads can still access and modify the heap. This proof is done via 7 layers of refinement. At layer 0, we have the concrete low-level implementation that only uses atomic CPU operations. At layer 1, we make lock-protected read-write accesses explicit, which allows us at layer 2 to form coarse atomic actions that are used in the barrier synchronization protocol. At layer 3, we reason about the safety of the collector making phase changes from being idle to marking the memory and finally sweeping unreachable objects. At layer 4, we changed the collection of gray objects from being a stack to being a set, which makes atomic actions commutative and allows us at layer 5 to form a big atomic action that does the whole scanning of the memory for unreachable objects in a single atomic step. Then at layer 6, we can let the garbage collector disappear completely and leave back atomic actions that allocate objects, read-write object fields, and check equality of objects. Now, this proof was done using an initial version of Civl and was maintained as we rewrote the verifier and added new features. A particular big improvement came with the introduction of yield invariants, which brought the verification time down from around a minute to 10 seconds. The second example is the Paxos protocol for reaching consensus among unreliable nodes in an asynchronous network. Here, the low-level implementation uses atomic actions for sending and receiving network messages and updating the local state of nodes. As a first step, we formed more coarse-grained atomic event handlers and changed the state to a more abstract protocol state. This is the level of detail you would usually find in a paper that deals with Paxos. Crucially, this first step does not yet reason at all about the correctness of the protocol. It only changes the state representation. Now, as a second step, we use the inductive sequentialization proof rule to reason only about particular sequential executions of the protocol, where the individual rounds in the protocol do not overlap. This allows us to have much simpler invariants compared to classical Paxos invariants that don't have to deal with these overlapping rounds. Now, the high-level specification that we end up with is a single atomic action that reaches consensus among all of the network nodes in a single atomic step. Besides our own experience, I want to highlight that several other researchers already used Civl to verify concurrent algorithms and data structures. This suggests that Civl specification and verification features are natural to users. Furthermore, the concept of layering allowed different developers to partition work with agreed-upon interfaces between layers. Civl is implemented as an extension of the Boogie verifier for sequential programs. The regular Boogie pipeline consists of a parser, a type checker, a VC generator that translates sequential procedures to logical formulas, and a module that interacts with the SMT solver. Now Civl adds two additional phases to this pipeline. The first one, the Civl type checker, is concerned with static analyses and the number of control and data flow analyses. For example, it checks that the layer annotations provided by the user constitute a well-formed layered program. The second phase, the Civl processor, is concerned with logical or semantical reasoning. It ensures that linear permissions are not duplicated, that mover types are correct, that invariants are correctly established and free of interference, that procedures refine their declared atomic actions, and that inductive sequentialization is correctly applied. Now, the output of the Civl processor is a collection of sequential procedures. So it essentially compiles away concurrency, such that the rest of the boogie pipeline can take over and interact with the SMT solver. As a result of decomposing Civl's proof system into many small checks, the user gets very targeted error messages in case any of the checks fail. Now, our paper provides more details on each component of the Civl type checker and the Civl processor. Here, I just want to highlight the -Civl desugared file flag of the tool, which outputs the sequential procedures generated by the Civl processor. Studying this output for a number of examples is a great way to learn the encoding. And this already leads me to the main message of my talk. Give Civl a try. Maybe you have a particular concurrent system or algorithm that you want to verify in Civl. Or maybe you have a new idea for a proof tactic that can be integrated into Civl. Or maybe you are building a verifier for a particular language that can use Civl as a backend verifier. Or maybe your verifier can use a particular component of Civl, like non-interference checking or mover types. In any case, our website provides tons of resources to get you started. Thanks a lot for listening.